Okay, here we are, rates of change. This is the last unit in the rates of change, and it was not included on your quiz. So instead, you will be doing an assignment, okay? Assignment number 2. Now, in this case, there is no new math really. It's just about applying what you've already learned in the context of some word problems, okay? So I'm going to go through this one word problem. It has 4 different sub-questions, okay? And these are very similar to what you will see on your assignment. So if you can go through this and you understand and you know what formula to use when and how to apply it, then you will be good on the assignment, okay? So the first thing I just want to go through the top here. So we have talked about the slope of the secant versus the slope of the tangent, okay? And in advanced functions, you guys did a lot of work with the slope of the secant, and that's what we call the average rate of change, because you're looking at how the curve has changed between 2 points on the curve, okay, taking their average. So the new thing we did with calculus, with limits, is this instantaneous rate of change, okay? And that's with the slope of the tangent at a specific point, okay? And just some new vocabulary. We also call this first principles. So basically the idea with first principles, oops, my alarm. The idea with first principles is that you sort of go back to square one and work with sort of key, I guess, foundational calculations to make something true. We will go from here beyond first principles to calculating derivatives directly. So the idea with the instant rate of change is basically doing a derivative from what is called first principles, okay? Just so you recognize it when that term is used. All right, so here is the problem. A rock is thrown from a cliff 80 meters high, 80 kilometers, my goodness. 80 meters high. After t seconds, the pebble is s meters above the ground. So if we're looking at our graph here, where's my cursor? If we're looking at our graph here, this is going to be t, and this is going to be s. Okay, so you can see it's thrown off the cliff, it goes higher, obviously it's thrown up, it reaches a maximum height, and then goes back down. All right, so the idea here is you want to calculate the average velocity, so you'll use the first formula between 1 second and 3 seconds. So basically you're going to find the average. We'll put VA for average, okay, between S at 3 seconds and S at 1 second. Okay, and then the denominator will be 3 minus 2. Okay, so you're going to have to calculate, plug in and figure out S at 3, S at 1. Okay, so I'm going to pause the video and give you a moment to do that, and then I will come back and move on, show you the answer, and move on to the next. Okay, here we are back. So I calculated S1 and S3. S1 is 105 meters per second. S3 is 125. So I'm just going to sub those in. Okay, you're going to end up with 20 over 2, which is obviously 10. Okay, and then don't forget this part, which is whenever you do a word problem, you have to write a concluding sentence. So therefore, the average velocity is 10 meters squared. Okay, you'll notice that at this point, the velocity is positive. So it's at this part of the graph right here. So you can see between 1 second and 3 seconds. Okay. So this is when the rock is still being thrown upward. All right. So you can see the slope is obviously positive. Okay. So now we're making a smaller interval. We want to find the average between 1 second, which we already know. We know that's 105. So we just have to calculate where it is at 1.5 seconds. So that's going to be about here. Okay, and you can see again, we're just obviously getting closer to the tangent at 1 second. Okay, so I'm going to pause this again and have you calculate this and be back. Okay, I'm back again. So I've just calculated by plugging in 1.5. So we know the distance off the ground at 1.5 seconds. So that's 113.75, and we have our 1 second value right up here, 105. Okay, so I'm just gonna plug this in. I know you guys are already ahead of me on this. So this will be 113.75 minus 105 over 0.5. Okay, so we have 8.75 over 0.5, which is 17.5. Okay, so again, don't forget your final statement. Okay, the average velocity is 17.5 meters per second. Okay, that's the units. And you can see up here, okay, whereas originally I was looking between 1 and 3 seconds, okay, which is obviously a shallower slope. Now I'm kind of receding back to where the velocity is going to be higher because the graph is steeper. All right, so 17.5. All right, so now what we want to do is we want to find the instantaneous velocity. So this is our limit 1, okay, h at 0. Okay, and again, we can call this kind of finding the velocity using first principles. All right, so we're going to use this second formula. All right, so I'm going to leave you to your calculations and I will come back. Okay. Okay, we're back. So you were calculating, well, you already have S at 1. It's going to be 105. Okay. And then we were calculating S at 1 plus H. Okay, so you just plug that in, simplify, and we get 105 plus 20H minus 5H. So that's here, minus the 105. As we've done in the past, you can see that the 105s cancel out. Okay, I'm going to pull out the H common factor right away. Okay, so you're left with 20H minus 5H squared. I pull out the common factor of H. This cancels out, and it's at this point that I can remove the limit notation because I can simply plug in. So I'm going to say 20 minus 5 times 0, obviously, is going to be 20. Okay, so at the instantaneous velocity at 1 second, you can see it's even faster, okay, as we're pulling back, all right, because we are getting closer and closer to that tangent line, which is steeper than any of the other intervals that we've used. All right, so don't forget to write your concluding statement. I will do that in a moment, but let's take a look at this next part. All right, so the question is, when is the pebble at rest? Okay, and rest does not mean when it reaches the ground. Yes, it will be at rest once it's hit the ground, but this is asking sort of mid kind of traveling. Where is it going to be 0? Okay, So that's going to happen when it's right at the peak point. So it's coming up, the velocity is positive, and then it's like basically an optimization maximum problem, okay? And when it's right at the peak at the vertex, it's going to change direction from going up to going down, and for the like millisecond of a millisecond, it's going to be at rest, okay? So we're looking, what is the time when the velocity, the instantaneous velocity, is equal to 0, okay? And that will be at that maximum point. And if you think about what you know about slopes, that's when the slope is going to be 0, meaning it's going to be perfectly horizontal, and that's going to happen at the maximum point. Okay, so when you do this, all right, you're going to use the same formula, all right? But instead of your unknown being the velocity, you can, and you plug in the time that you know, okay? Now the unknown is going to be the time, all right? So we're going to plug in 0 here, all right? I'm going to go off to the side. I'm going to, I know S at t is just going to be the regular formula, and I'm going to keep t in there. And so I have to figure out what S at t plus h is, all right? So I will be back. And you can go ahead and do this. All right, let's see where we are. Sorry, it's a bit messy because this is a very long polynomial. All right, so I put in t plus h into our formula, expanded it out. It could not simplify all of the terms. None of them are common, so we can't simplify it all. But when we get to this point, once we plugged it into the limit equation, okay, notice we set the velocity to 0. Okay, so we're gonna, h will disappear. I think that's probably not the math word, but anyway, so you'll see, although h is in there just as a helper variable, basically, through this limit, the unknown that we're solving for is actually the t. So we'll get to the end, and we will have just a very simple equation to solve for t. All right, so let's do our canceling out. So my 80s can cancel out. My 30t can cancel out. All right, my negative 5t can cancel out. All right, so let's move down to the next line. And if you look at what we have left, okay, we have 30h. Let's try that again. 30h. We have 10ht. Oh no, I copied that down wrong. It should be a minus. Please make sure you don't copy my mistake. All right. So minus each 10ht. And then we obviously have our minus h squared. Oh my goodness, where's my brain? Okay. You guys probably saw these mistakes a mile away. All right. Admittedly, it's very early in the morning, but no excuse. All right, I made that mistake over here too. So, corrections. Okay. All right, so this is what we have. We have 30h minus 10ht minus 5h squared. All right, so I am going to pull out my common factor of h at this point. So I'm going to have 30 minus 10t, Okay, so once we remove the h, okay, minus 5h. All right. Okay, so I'm going to cancel the h out. Okay, and now we can substitute without it being indeterminate. So I'm going to come outside of my limit now. I don't need that anymore. And I'm going to replace h with 0. So remember, all along here, the velocity is 0. So I'm going to have 30 minus 10t minus 5 times 0. So obviously that will be equivalent to 0. All right, so I can move my negative 10t over to the other side. So I'm going to have 10t equals 30, divide both sides by 10, and I get that the time is going to be 3 seconds. So when is it equal to 0? Basically, when is the pebble at rest at the very top at the maximum? Where is the maximum? Should be at t equals 3. So let's look back to our graph, and we can see t equals 3. That's exactly, okay, that vertex point. All right. So let us just be finished. Okay. So we'll write the final statement, and then you guys can move on to the assignment. Okay. So the pebble is at rest at 3 seconds. Thank you. Okay, there's our concluding statement. All right. Good luck with the assignment.